Hello everyone and welcome to the fourth lecture in MEC 3430, Automotive Engineering Fundamentals. On this lecture, we're going to look at an introduction to spark ignition and compression ignition combustion. Now it's important to note that during this lecture it is only an introduction. You'll be taking a full course on internal combustion engines, and the combustion process is going to form a large part of that particular course. So last class we looked at internal combustion engine configuration, dynamics, and valve train. So we looked at common configurations, we looked at forces and dynamics, and we looked at valve train configurations as well. In this lecture, we're going to look at intro to SI combustion. We're going to look at the main processes that occur. We're going to look at mixture prep and chamber design. We're then going to look at the same thing as an introduction to compression ignition, the main compression ignition processes, droplet combustion, and then finally compression ignition chamber design. Okay, so spark ignition combustion. So this uses an external energy input. Generally it's electrical via spark from a spark plug to initiate combustion. This combustion transfers energy into heat, and the heat is transformed into work. Now that is common to compression ignition as well. So when we look at what's called a pressure trace, this is the pressure inside the cylinder as the cylinder is rotating relative with crank angle degrees relative to top dead center. We see we have our pressure increasing due to compression. We then have ignition, large spike in pressure. Pressure eventually goes down during the power stroke, and then we have the exhaust valve open and pressure returns to atmospheric. So when we have spark ignition, there's really three things that we have to worry about or consider. Ignition and flame development, so that's the initial starting. We need to worry about flame propagation and then flame termination. So ignition and flame development. So as we said, combustion is started by an electrical discharge across electrodes of a spark plug. So we need a spark plug to start off the whole process. We generally have this spark occurs between 30 to 20 degrees before top dead center. So ignites the air fuel mixture in the vicinity of the spark. Now how come we ignite between 30 to 10 before how come we started before top dead center? Well, because it takes time for the flame to actually develop. The flame doesn't develop instantaneously. When we need time for that flame to get developed, so by the time we're at the top of the compression stroke, the flame is well developed and we're ready to release our maximum power in the power stroke. So that's why we go between 30 to 10 crank angle degrees before top dead center. Now if we do it too soon, we're going to have more negative work. As you can imagine, if the combustion happens too soon, that means we're going to get a pressure spike while we're still trying to compress the intake charge, or we're still during the compression stroke. If we have a large pressure spike during the compression stroke, that means the piston or the engine is fighting against this pressure to be able to compress the intake charge. And this is negative work. If we spark too late, well then we won't have enough positive work. We won't have a big enough pressure spike during the power stroke. So there is an optimum timing. And this optimal timing is going to be investigated more during the internal combustion engines course. And as I said, we ignite before top dead center because flame propagation actually takes time. So after the spark, what happens? Well, we get this spherical flame front develops and moves outwards towards the boundary of the chambers. So we have this ignition point, and we have this flame that will propagate from the ignition point towards the cylinder and boundaries and the top of the piston. So flame is slow initially due to being small and surrounded by cold, unburnt gases. So initially the flame is pretty small and it moves slow. So once we're out of the initial flame development stage, we're then into flame propagation. So after about 5 to 10% of the fuel is burned, the combustion process is well established and flame moves quickly. Turbulence then starts to impact the flame, and this increases the flame due to turbulent eddies creating increased flame area. And the flame can actually move approximately 10 times faster when it's a turbulent. So if we look at a laminar flame, the flame can only move based on the area between the burnt gas and the unburnt gas. And if it's laminar, we have a smooth circular front. We have a turbulent flame, well, we have this wrinkled, we have all these wrinkles, and these wrinkles add additional area for combustion to occur. And that makes turbulent flames move much faster than laminar flames. Again, this will be covered more in the internal combustion engine course. But the idea here is turbulent flames are much faster than laminar. So flame propagation in spark ignition is mostly due to turbulent flames rather than laminar. So during flame propagation, there's also some other considerations that have to be made. Depending on the fuel composition, air-fuel ratio affect this flame's speed. So if we have a rich air-fuel ratio, then we're actually going to have a faster flame. So local air-fuel ratio in an engine is important, particularly in a spark ignition. We want to have a very well-mixed charge because we want the flame to propagate at an even speed. We don't want it to speed up, slow down, as it goes through pockets of different air-fuel ratios. If we look at the burn angle, so degrees of crank angle rotation, we look, most typical combustion duration is about 25 crank angle degrees. As we look here, going from 5% burn to 95% burn. Now, it generally takes more CAD, crank angle degrees, for combustion as engine speed increases, because we have more competition between, so we have this competition between more turbulence and more crank angle degree seconds. So as we get more speed, we get more turbulence, which means we're going to increase the actual physical time, or we're going to reduce the time it takes for the fuel to burn. But remember, since we have more speed, crank angle degrees don't last as long in terms of physical time. One crank angle degree is less seconds at high engine speed than it is at low engine speed. So at higher engine speed, yes, we have lower physical time per crank angle degree, but we also have higher turbulence. So we have this competition between turbulence and more crank angle degrees per second. We can also advance the timing as engine speed increases, i.e. start the ignition, set the spark off earlier, so more before top dead center crank angle degrees, and that can help alleviate this problem as well. Then we have the flame termination stage. So at about 15 to 20 crank angle degrees after top dead center, 90 to 95% of the fuel has been burned and the flame has reached the outer walls. The remaining unburned gas in the vicinity of the walls is called the end gas. So due to being near the wall, we don't have a lot of turbulence. Remember, we have a no-slip condition at the wall, and this cannot aid in burning the end gas. Additionally, the wall acts as a heat sink and reduces temperature. So lower temperature, more lower turbulence equals a much slower flame. So the flame termination doesn't release much energy due to slower flame, thus lower rate of energy release. And due to radiation, the end gas is still fairly hot and can auto-ignite, leading to knock. So in other words, we don't want to have a ton of end gas left in our cylinder because we're not going to get much energy release from it. But we can still have it auto-ignite, which leads to knock, which we definitely don't want. Now, what is engine knock? Well, engine knock occurs when a portion of the air-fuel mixture ignites ahead of the flame front. So we look at this diagram here. Here's the spark plug and here's the burnt gas. Here's the flame front. If we had a pocket in the unburned gas that starts igniting, that is knock. So in other words, when we have the unburnt gas mixture ignite ahead of the flame front, that is bad. This results in high pressure spikes and potential component damage, and also an audible noise, or knock, hence why it's called engine knock. So we want to avoid engine knock at all costs because it's not only bad for efficiency, but it also could potentially damage your engine, and it can slowly damage it over time. Now, most modern engines are equipped with electronics to detect knocking, and they can retard the timing to avoid this knocking occurring. Okay, so we talked about the combustion process with the fuel and air in the cylinder, but how do we get that fuel and air, and how do we mix it in the cylinder? So conventional spark ignition engines use what's called a homogeneous charge. So that's air and fuel is fully premixed and enters the chamber at the same time. So homogeneous charge to ensure consistent flame propagation rates. Because remember, flame speed depends on the air-fuel ratio. So fuel delivery in the intake manifold is vapor, liquid drops, and liquid film. So it's a really complicated process in that we don't have fuel just being delivered in as a gas. We have it as a vapor, a liquid drop, and a liquid film. So it's actually quite complicated in getting the correct amount of fuel into the engine. Now there's two ways to add fuel to the engine. There's the carburetor method, and there's the fuel injector. Now the carburetor is quite an old technology, and it's really no longer used in most automotive applications, but I'll briefly discuss it. So what's a carburetor? Well, it uses a Bernoulli principle via Venturi to suck fuel into the air intake stream. So there's a reduction in cross-sectional area that accelerates the flow. So air is coming in, there's a reduction in cross-sectional area that accelerates the flow. That means we get a low pressure area. This low pressure area entrains fuel from a different tube in the stream. So essentially it uses Venturi to create low pressure and then suck fuel into the stream. Now the problem with this whole carburetor design is you cannot separately change the air and fuel flow rate. They are coupled. If you have less air coming in, you have less fuel. You can't decouple to change the air-fuel ratio. Also, there's a minimum differential pressure needed for fuel to flow. In other words, this can't work at very low flow rates. So there's kind of a minimum that has to be flowing. So if a carburetor, if your engine drops below a certain RPM or a certain amount of air inflow, you're not going to have any fuel and the engine's going to stall. So generally, you can't have very low idle speeds of your engine. This means this is worse for fuel efficiency and also for emissions. It's also bad because we can't achieve tight control of the air-fuel ratio. And this is bad, again, from a flame propagation and also emission standpoint. So generally, carburetors are not used in modern vehicles. They're still used on small internal combustion engines that might be used for a lawnmower, a string trimmer, or what might be more commonly referred to as a weed whacker. Snow blowers will also use carburetors, although some snow blowers now use fuel injectors as well. But generally only small engines use carburetors, and only single cylinder engines generally use carburetors nowadays. Okay, so carburetors have mostly been replaced by a fuel injector. So fuel injectors, they are electronically controlled. They are not the same as some CI engines that use mechanical fuel injectors. So generally all fuel injectors in spark ignitions are electronically controlled. They're operated by a solenoid, and there's a signal to inject the fuel given by the computer control unit or computer module of the car. So essentially you have better control over the amount of fuel that's being injected into your intake. Now there's two types of fuel injection. There's single point and multi-point. Single point is, as it sounds, fuel delivery to intake system at a single location. Now this is very similar to a carburetor, because essentially a carburetor delivers fuel in the intake in a single location, except the total amount of fuel can be controlled much better. So we can control the total air-fuel ratio, but we can't control the air-fuel ratio per cylinder. It's still a global air-fuel ratio, if you will. So that's where multi-point injection comes in, is where fuel is delivered to the engine at multiple locations, with each cylinder having its own injector. So this way you can have precise control of fuel to each cylinder, which gives you much better control over the local air-fuel ratio. So the injector is generally at the intake port on the cylinder head, and the fuel is sprayed at the back of the hot intake valve to promote fuel vaporization and mixing. So not only do we have better air-fuel ratio control in each cylinder, we also get better mixing, because we can put the injector right at the intake port on the head, and we can spray the fuel into the hot intake valve to promote fuel vaporization and mixing. In other words, multi-point fuel injection is just a much better way to make sure the air and fuel are mixed as well as possible, and that we have tight air-fuel ratio control. So we're now going to talk about combustion chamber design for spark ignition engines. So there's 6 kind of goals that we want to be able to do when we design spark ignition combustion chambers. We want to maximize the flame frontal area and reduce maximum flame travel distance. The longer the flame has to travel, the longer it's going to take, and that's bad. We want to maximize the flame area because it's going to travel faster. We want to optimize mixing of fuel and air. We want tight control over that air-fuel ratio. We want to maximize N-gas quenching. We don't want any knock while minimizing unburned hydrocarbons. So essentially we want to quench the N-gas, but we don't want to quench much of it because we don't want to emit unburned hydrocarbons. We want to optimize the octane number to engine compression ratio. The spark plug and exhaust valve are close together, and this is for flow characteristics. And finally, we want to optimize the bore to stroke ratio for application. Square is usually good. So what does square mean? Well, over square is a short stroke, long bore. Under square is long stroke, small bore. So square is generally equal stroke and bore. Okay, so we said mixing is very important, in spark ignition. Now, most mixing in spark ignition is done in the intake manifold. It's not done in the cylinder. So turbulence generation inside the cylinder is mostly used for flame propagation. So not so much for mixing, but more so for flame propagation. And really in a spark ignition engine, there's only two ways you can really generate turbulence. And that is swirl, which is actual fluid motion around the cylinder's central axis, and tumble, so in-cylinder flow, which rotates around an axis perpendicular to the cylinder axis. So we have swirl and we have tumble. Now, it should be noted that these turbulence generation methods are not only for spark ignition, they're also relevant to compression ignition. Although compression ignition generally has some added features to create additional turbulence as well. So in a spark ignition, these are the only two types of turbulence you're going to generate. There's another type of turbulence you can also generate, again in spark and compression ignition areas, is called squish area. So an area on the outer edge of the piston head where mixture is highly compressed near top dead center. This high compression causes the mixture to be forced out of the area with high turbulence. So if you create your cylinder to have these squish areas or squish bands, this is going to generate turbulence, and it's going to generate it right as you're at top dead center, which is exactly as when the combustion is trying to propagate throughout the cylinder. So it works out quite well in terms of generating turbulence in the cylinder. So let's look at some combustion chamber variants. We have A, which is a wedge. We have the hemispherical, which is very common and was popularized during the muscle car era. We have bowl and piston type chamber, and we have the bathtub head. Now, the main point with all of these is that they all have a short maximum flame travel. The spark plug is close to the exhaust valve. There's a squish area for turbulence, and we get a well and cooled end gas. So they all have these four properties. Now, we've talked about the importance of mixing the fuel and air and how most of the time the fuel and air is mixed before it gets into the cylinder. Well, to be honest, almost all modern gasoline or spark ignition engines, particularly ones that you would buy after about 2020, so in other words, any new vehicle nowadays, they're actually not going to use injectors into the intake manifold anymore. They're going to use what's called gasoline direct injection. So in this case, instead of having a fuel injector with multi-point fuel injection, we'd have the fuel injectors in the intake manifold spraying at the back of the intake valve. In gasoline direct injection, the fuel injector sprays the fuel directly into the combustion chamber. Now, this kind of goes against everything we just said about tight air-fuel ratio control, et cetera, et cetera, et cetera, because now we have a stratified charge, i.e. it's no longer premixed, it's no longer homogeneous. We have the air and fuel coming into the cylinder separately. Now, the advantage of having the air and fuel going in separately is you can use higher compression ratios while avoiding knock. In other words, we can control how much fuel is in the engine during the entire power, compression, and power stroke. So we not only have the control over the amount of fuel, but we have more control over when and how much fuel is in the cylinder. Now, this actually allows for increased efficiency, which will reduce CO2 emissions. And we know CO2 is a greenhouse gas and is linked to climate change. So this is kind of a compression or spark ignition engine operating like a diesel engine. We no longer have the fuel being injected into the intake, we have the fuel being injected directly into the cylinder. So this allows for higher compression ratios, which gives us more efficiency. The problem, though, and not many people mention about GDI, is that this gives you higher carbon monoxide, higher unburned hydrocarbons, and higher particulate matter emissions. In other words, all the problems with diesel engines or traditional compression ignition engines, well, now GDI engines have those problems. So all the problems that only diesel used to have, gasoline now has as well because of this gasoline direct injection. So it's kind of odd that diesel engines are being banned all around the world when now we've basically converted all our gasoline engines to operate like a diesel. In my opinion, the only reason diesel engines are dead is because of Dieselgate, i.e. the scandal with, I'm forgetting now if it's Volkswagen or Volvo, but basically the scandal of either Volkswagen or Volvo where they cheated the emission tests in order to pass their vehicles. Essentially what they did was they had a computer logic in their vehicles where if it knew it was going through an emission test, it could detect it, and then it would implement all its emission reduction strategies, which would also reduce engine power by a good percentage. When it knew it wasn't during an emission test, i.e. during regular driving, it would disable all the emission reduction strategies and allow the engine to have more power. This just happened to be a diesel engine that where this Dieselgate or these emission testing kind of spoofs, or how should I say, trickery was being done. So diesel engines ended up getting a bad name. In all truth, diesel engines actually are much more efficient than gasoline engines, even with gasoline direct injection. In other words, the world is actually better off from an emission standpoint to use diesel engines with appropriate exhaust after treatment systems to help clean up the exhaust. Essentially what we now have is gasoline direct injection, which is operating like a diesel and still requires all the diesel after treatment systems that a regular diesel engine would require. So in other words, we threw out diesel because it was bad and we replaced it with something that is essentially diesel. Anyways, politics at work. All right, back onto our regularly scheduled program for this lecture. I am now going to talk about compression ignition combustion. Okay, so in compression ignition combustion, ignition occurs spontaneously due to high pressure temperature from compression, i.e. there's no spark. It just happens because we've compressed this air and fuel so much that we just get the mixture starts, or the air and fuel start to ignite. In this case, we don't have a single flame propagating. We actually have multiple flame kernels spontaneously combusting in the cylinder. So there's no flame propagation. We just have small little pockets of flames all over the cylinder. This is a stratified charge. In other words, all mixing is done in the cylinder, just like a gasoline direct injection. In this type of engine, mixing is critically important. You need lots and lots of turbulence to make sure you can mix as fast as possible. Unlike spark ignition, where the start of ignition is controlled by a spark, in compression ignition combustion, the ignition timing is controlled by when you inject your fuel. So it's a different control mechanism. That's one of the main differentiators between spark ignition and compression ignition. Spark ignition, your control mechanism is the spark timing. Compression ignition, your combustion control is the injection timing, when you inject the fuel. Because as soon as you inject the fuel, because of the high pressure and temperature, you're going to get combustion. So what does this combustion process look like? If we look at the curve with the dashed line, that is with no combustion. So generally we reach higher compression ratios or higher pressure even without combustion. At point A, we have our start of injection. We have an injection delay. We finally have our combustion takeoff, where we have a very large pressure spike. Then we have controlled combustion, and finally final combustion. And eventually the pressure drops off back to atmosphere. So one of the main characteristics that differentiates spark ignition and compression ignition is that the pressure spikes are much higher. We have a much higher pressure in compression ignition engines than spark ignition. So there are 5 main processes that we need to care about in compression ignition. That is atomization of the fuel. So we sprayed in the diesel fuel into the cylinder. It comes in as a liquid. We need it to be a gas so that it can burn. Atomization. It comes in as a liquid, but we want the liquid to be in as small a droplets as possible. Smaller droplets means higher surface area, which means more area for combustion. We then need to vaporize these fuel droplets. So once the droplets have come in, they've atomized into small droplets. We need to start vaporizing them so they can start mixing with the air. Then we have the mixing of the fuel and air. We have the auto ignition. Then we have main combustion. Now, unlike spark ignition combustion, where it's a flame propagating throughout the entire cylinder, in compression ignition, we have multiple droplets that are combusting simultaneously. So it's actually droplet combustion that controls compression ignition combustion rather than flame propagation. Now, droplet combustion is quite a complex phenomenon. Picture here, here's a droplet we have, which is maybe some liquid diesel. And around it, there's going to be a flame front. And then between the flame front and the droplet, you're going to have different species concentrations. And then you have different concentrations outside the flame front. This is a pretty complex phenomenon that's actually going to be handled mostly in your fourth year internal combustion engine course, but just note that in general, compression ignition combustion is much more complicated than spark ignition combustion because we have these multiple flame fronts around droplets. What are some requirements for combustion ignition chambers? Well, we want a short ignition delay time. We don't want to have a long delay between injecting the fuel and ignition. We want combustion to occur around top dead center, so our pressure spike is giving us positive work. We want the combustion to occupy the entire volume of the combustion chamber. So unlike spark ignition, where we only want combustion to happen at the propagating flame front, in compression ignition, we want combustion occurring in the entire chamber. We want every single droplet burning as fast as possible. We want to ensure we have lots of turbulence generation. Again, that's what we need to make sure we have tons of mixing. And then 5 really follows from 4. In that 5, we want to optimize the fuel and air mixing. Now here's a list of some type of chambers that can be used in compression ignition engines and how they try to generate turbulence. There's direct injection chambers, which are A and B. That's where injection is done directly into the chamber. And you can see they use fancy designs of the piston top to create turbulence. We have either what's called an open or an M-type piston or cylinder design, and it uses the shape on the piston itself to create turbulence. We then have different types which are called indirect injection, i.e. there's injection of the fuel into this kind of pre-chamber type thing, which is then goes into the main cylinder. So we have a pre-combustion where we actually have some combustion going on in the pre-chamber before it enters the main chamber. We have a swirl chamber, we have an energy cell type chamber, and then finally a spark assisted type chamber where we actually have a little spark in the pre-chamber to help kick off combustion. So these are different strategies for turbulence generation and also for starting off the combustion process. Now we're not going to go into the details of pros and cons of each of these in this particular course. Okay, so ticket out the door. Again, something you learned today, something that the explanation was not clear or something that was confusing. And that is everything for this lecture. Thank you very much for attending this lecture and listening in. This is our last lecture on internal combustion engines, and for the remainder of this course we'll look at all the other main components in a vehicle, such as the transmission. We're also going to look at suspension and steering. We're going to look at hybrid power trains. We're going to look at the brakes, body, and chassis. And finally, the last lecture is going to look at autonomous vehicles. All right, thank you very much for your attention, and goodbye.